That is, here is just the set of samples multiplied by f. Okay? So sampling is just multiplying your continuous signal by this discrete comb. This is why we had to introduce the notion of multiplying functions and the notion of a comb. Sampling is the multiplication of your signal by a comb. Now, when I multiply in space, what do I do in frequency? I convolve. Remember, convolution in space is multiply in frequency, and multiply in space is convolution in frequency. So what I'm going to do is I'm going to convolve the Fourier transform of f with the Fourier transform of the comb. I'm just showing the power here, and I get that. Okay, so this is the convolution, and you'll see if I just take this function and I slide it along, I'll reconstruct it here, reconstruct it here, reconstruct it there, and that's what this is showing you. Okay, so that's the Fourier transform of the multiplication of the comb times the function. Just copying that bottom row. If this function is limited, in fact, I can show it down here like this, all right, then if I could pull out that part of the signal, the part of the signal that's frequency is just within some range, then I would be able to get back what I wanted, right? I would be able to get back the original spectrum, which would give me back the original function. So this is no problem if this outer edge is small enough. That is, that the maximum frequency of my signal is low enough for the comb filter that I used. Exactly what is that small enough? Well, here it's written like this, okay? If my comb filter is spacing m, so then the comb of my Fourier of the Fourier of the comb is 1 over m. Half this distance here is 1 over 2m, okay? If the maximum frequency of that function, let's say is w, for bandwidth, is w, if that's less than 1 over 2m, then I can reconstruct that original signal by looking at just this part. That is, nothing has contaminated that inner part. So if there's no overlap, if w is less than 1 over 2m, the original signal can be recovered from its samples by low-pass filtering, which we'll talk about in a minute. So those of you that know something about Nyquist sampling, so you know that if I want to recover, say, something up to 20 kilohertz, right? 20 kilohertz about the extent of human hearing. I would need to sample at least 40 kilohertz. By the way, CDs, like we were talking about, sample at 44 kilohertz. Why? So that we can recover everything up to 22 kilohertz, which is the extent of human hearing. So as long as my frequencies are low enough, I'm okay. But what if they're not low enough? What happens? Well, now, let's suppose I have a higher frequency thing. So this is some random function, and it has some high frequency. So here's its f of u, and you see its w goes out a little bit further. If now I multiply that by the same comb of m, I'm going to convolve this thing with that 1 over m comb that I had before, and I'm going to get this part here. Now remember, these things actually sum. I'm drawing each individual component, but in reality, this thing would sum and come back up here, right? So these things would sum and come back up there. And this area right here is where this energy has folded back on itself. It's overlapped, and then they're going to add, okay? That high frequency that was really this little edge thing here, okay, or you think of it there, is pretending it's low frequency. That's the aliasing. And once you've aliased the signal, once you've done this operation, you cannot undo it. The high frequencies have pretended that they're low frequencies, and you can't separate them out from real low frequencies. You have to remove the high frequencies before you do the sampling in order to remove the aliasing. So how might you do that? Okay? Well, how do you remove high frequencies? Well, we know how to do that. We convolve with H. Maybe it's another Gaussian. What does that do? That reduces the high frequencies. So the frequency spectrum of the convolution of f and h has much less high frequency. So that H is what's referred to as an anti-aliasing filter. And it has the net effect of trimming the high frequencies of the original signal. So that then when I do the multiplication by the comb, which is shown here, right, I'm now convolving that with a comb filter in the frequency domain, but I don't get that overlap, right? So no aliasing goes on, all right? And then to recover the signal, whatever I get after I reconstruct from that using the new sampled convolved function, I can throw away any high frequencies because those are not real. That is, so just the way we did with the CD, right? We low pass filtered the microphone, did a to D conversion to get some digital samples. We did a D to A conversion to get an analog, and we knew that any high frequency that showed up, that's not real. Okay, we could low pass that away and recover the original signal. So that's summarized here in terms of aliasing. When I don't have an anti-aliasing filter, I get these overlap regions that cause me to get aliasings that I cannot remove once I've done it. But with an anti-aliasing filter, I don't get that overlap. So that's the mathematics behind aliasing. We can see this going on in images. So here's a nicer picture showing you aliasing in images. So you can see what's happening is that this is a radial sine wave. And you can see as you get closer and closer, the pixels are supposed to be wiggling faster and faster. And eventually, I run out of pixels. Okay, I don't have enough samples to get how quickly the thing varies. And so that's an example of aliasing here. So what is its impact on you? Well, its impact on you is you have to be a little careful how you treat your images. For example, and this comes from Steve, all right? Suppose I've got this image, a beautiful Van Gogh picture, and suppose it's too big to fit on a screen. I want a smaller version of it. How can we reduce it? I don't know, make it half the size or a quarter of its size to do that. Well, one obvious way would be to throw away every other column and every other row, right? Just throw those away. And that's called image subsampling. Now, by the way, here it says by half. What it means is I throw away half the columns and half the rows, which of course is actually a quarter size smaller, right? But half meaning half the rows, half the columns. If I did that again, I would now have 1/4 the total rows, 1/4 the total columns, 1/16 the size. I could do it again, 1/8. In fact, you might start to notice that this is already looking a little ugly. And in fact, to make it clear exactly how ugly it is, let me blow up the half, the quarter, and the eighth by zooming in on both of them, just blowing up the pixels. And you'll notice this is atrocious, okay? The 1/2 one doesn't look too bad, but remember here, we've only taken 1 out of every 8 columns and 1 out of every 8 rows, and then we blew the thing back up. And you can see that this does not look like a blurry version of the original, okay? And the reason is we have aliasing. We have sampled too infrequently for the amount of variation that there is. Essentially, things wiggle in here more often than 1 out of every 8. And so if I just take 1/8, right, I'm not capturing all the wiggles. So what's the right thing to do? Well, we need to do that anti-aliasing. We just learned that. So a simple one is to do Gaussian, okay? So what we'll do is we'll filter, right? So we'll take the Gaussian and then take every other row, all right? And then if you want to be not so clever about this, you could do a Gaussian of that and take every other row of that to get the 1/4. And you could do the Gaussian again and do that. Or what you could do is you do a much bigger Gaussian to begin with and take 1 out of every 8. You can convince yourself that mathematically these are going to be equivalent. When I do that and I blow up the Gaussian 1/8, you'll see that this actually looks pretty much like a blurry version of that, right? Compare this to what we did with the subsampling, right? So here's sort of our original. Here is the Gaussian 1/8 4x zoom, and here is the subsample 4x zoom. And you can see that the Gaussian does a much better job in doing the reduction, and that's because it's been anti-aliased. So if you're doing computer vision and you decide, you know what, I've got this huge 1920 by 1080 image coming in, but I'm just trying to recognize faces, right? And my faces are going to be, 100 pixels big, let's say. And you say, you know what I can do is it's going to be expensive to do that face recognition. We're going to talk about face recognition towards the end of the class. It's expensive to do that over the entire image when it's so big. Let me make the image, 1/8 its size this way, 1/8 its size that way. And I'll make my faces smaller and look for them that way. You know what? That will work pretty well if you do this, if you do anti-aliasing. If you just pull out the arbitrary pixels, right, you're going to make a mess of the whole thing. You'll get aliasing, and then the faces won't look right. So that's why doing this kind of stuff matters even in computer vision. That almost ends our lesson on frequency. There's just one more thing I wanted to talk to you about today because it's so prevalent in the processing that you're going to be doing. Some psychophysicists, Campbell and Robson, studied a long time ago the contrast sensitivity of the human vision system, not just the eye. Now, what you're looking at here is a curve where frequency goes up to the right and contrast goes up down. And probably, if you're like me, hopefully you're not like me. One of me is way more than enough, as my children will tell you. But anyway, if you're like most humans, you probably can see this stuff really well, but not so much up there. And somewhere around there, that curve is where the fall off is. That essentially, lower contrast up here, you can't really see the variation. Same thing with this high contrast. Okay, your eye is sensitive in different ways. So what this means is that some frequencies matter more in terms of the importance to you in an image. Okay? In particular, if I were to leave out a bunch of that frequencies, so that is, if there was low contrast at the high frequency, you wouldn't even know. So you can use that to do image compression. You probably have heard of JPEG. Probably have JPEG images all around you. Okay? JPEG uses something called the discrete cosine transform or variations thereof. Basically, a way of thinking about that is they take a little 8x8 region of the image. So you carve the whole region up into little 8x8 segments. And then it takes as a basis set these sinusoids and cosinusoids, right? So here we have the ones that are vertical, here we have ones that are coming down, and here we have the product of them. And you can see the lower frequencies are in the top left-hand corner, and the higher frequencies are in the bottom right-hand corner. So what you can do is you can say, how much of each of these do I need to make the picture? And you can actually order them, right? You can sort of go through them and order them this way, with the idea being that the top left-hand corner might be, in fact, go back here. You see how this is a constant? Okay? So that's just the average of the picture. So the top left-hand corner, what's sometimes called B00, that's just the DC component, the average. And then as you get further and further, you're getting the higher and higher frequencies. So the top left-hand corner represents the lower frequencies. The bottom right-hand corner represents the higher frequencies. Now, what we said before is we don't have to represent the higher frequencies that well, right? Just sort of the high contrasty components of it. So one way of doing that is saying, what if we encode these coefficients better, more bits, than these coefficients? And that gives you what's called a quantization table. And DCT, discrete cosine transform, does the compression by, so what this 3 means is we keep the coefficient, say, to the nearest 3 values. So if you're thinking of this in bits, you can shift it over by 2. The idea is that you round this to the nearest 3, whereas this is rounded to the nearest 31, okay? So in other words, you're doing more representation of the top left-hand corner than you are of the bottom right-hand corner, okay? And so what that means is you lose information, but you're mostly losing the information down here, okay? And the same way, by the way, that you do the inverse Fourier transform, given the spectrum, you can reconstruct the signal. The same is true of the DCT. IDCT, inverse DCT, given those coefficients, I can reconstruct the image. But now, instead of maintaining all those coefficients exactly, I'm only going to keep more information about the low frequency coefficients than I am about the high frequency coefficients. And that works really well for the human vision system. And so if you take a look at your average JPEG image, and here's an example stolen from the web somewhere, okay? So they used 89,000 bytes of information to represent this picture. using just the raw intensities, and 12,000 bytes here, so this is a ratio of what, 7 to 1, using DCT coefficients, the JPEG standard, all right? The reason it works